Here we have an example where we have bivariate data, temperature, small t, and mass, small m. The data is coded using the change of variables. So t becomes x, and log of m becomes y. The equation of the regression line, which is just a line of best fit on y and x, is found to be this. Part A, given that the data can be modeled by an equation of the form m equals a times b to the power t, where a and b are constants, find the values of a and b. So we've told that it can be modeled by an equation of this form. So what I'm going to do is start off writing that form down, and then I'm going to derive the equivalent of the regression line and then compare the numbers to see what a and b would have to be. So by logging both sides, I've chosen to use log base 10. Could use any log really, but I've chosen log base 10 here. When you can't see a number underneath the log as a subscript, it means log base 10. On the right hand side here, make sure you don't make the common mistake. This right hand side here is not t times log of AB. Instead, we can use the law of logs that allows us to break it apart into log A plus log of b to the power t. Then on the right hand side, we can use the index law for the final term, it becomes t log b. So now let's compare that with the regression line of y on x, written it directly underneath. So by comparing, we can see that log a must be minus 0.3705. Rearranging this, that means a must be 10 to the power minus 0.3705. That's just rearranging logs from pure maths. And we get 0.426 to 3 significant figures. Again, by comparing, remember t replaced x, or rather x replaced t. So x and t are pretty much the same thing here, which means that 0.0636 must be the same as log b. That's where I get this from. 0.0636 is the same as log b. By solving for b, b is 10 to the power 0.0636, so there's 1.16 to 3 sig fig. That's part A. Find the values of a and b. Done. In part B, give an interpretation of the constant b in this equation. So this equation, m equals a times b to the power t. Remember we found that b was 1.16. Let's just think about what happens as t increases. So what is m when t is 1? I'm using this notation here to mean the value of m when t is 1. So when t is 1, we just get a times b. And I've used the value for b, 1.16. I could have also used my value for a, 0.426. I just haven't, so I'm focusing on b. What would we get when t was 2? Well, we get a times 1.16 squared. I've just let t equal 2 in this equation here. When t is 3, we'd get that, and so on. So think about what's happening as t increases by 1. Each time, it's growing by a multiplication of 1.16, which you could say it's increasing by 16%. So let's put that into words now, give an interpretation of the constant b in this equation. So in words, and this is what you might write for your answer, an increase of 1 degree Celsius in temperature will increase, we must see the word increase, the mass of chemical by approximately 16%. That comes from multiplying by 1.16 each time. It's actually a geometric sequence, increasing by 16% each time t increases by 1 degree C. Another way you could word that, you could also say it is the rate of change of m per degree. or the rate of change of mass per degree.